Alright, in this video we want to set up a Riemann sum to compute the definite integral. So you may recall from the notes that our left or right hand endpoint rules qualify as a Riemann sum, and those are generally the ones that we use. So to do a definite integral right now, we want to set up a sum to compute the area. So we begin by computing delta x, that's the width of the interval. So it's from 0 to 3, so 3 minus 0 over n should be 3 over n. And then remember, xi is just going to be your starting point plus the delta x times I, which in this case would just simplify to be 3 over n I. A little bit clearer there. 3 over n I. Okay. And then we take that delta x and we plug it into our function. Our function is x cubed minus 1, so it would be 3 over ni cubed minus 1. We go ahead and simplify. 3 becomes 27, n becomes n cubed, I cubed minus 1. So we now have our f of x function, and at this point we're ready to plug all this into the summation. So it's sum, I goes from 1 to n, of f times delta x. F times delta x. And then we multiply out 3 over n. That's going to go 3 into 27 will make that 81. N to the fourth to go with the I cubed. So we can go ahead and actually save a little bit of writing. I'm just going to pull that out. 81 over n to the fourth. My constant part there. Times the sum of the I cubes. And then also take the 3 over n times the 1. And that's just going to be 3 over n times the sum of the ones. And then we go back and pull out our formulas for the sum of the cubes and for the sum of 1. And then we just evaluate each of those things. So we would have 81 over n to the fourth, and then the formula for the sum of the cubes, n squared, n plus 1 squared, all over 4. All over 4. And then 3 over n times 1, well, if you add 1 up n times, you're just going to get n. So we'll have 3 over n times n. And then we can simplify here, cancel out an n squared with an n to the fourth to leave 2 in the bottom. Cancel the n and the n. That'll just leave us with 3 for that part. Now here we can multiply out 81 times the stuff at the top. That n plus 1 squared is going to be n squared plus 2n plus 1. So each of those things are going to get multiplied by 81. So when we do that, we get 81n squared plus 162n plus 81. And then that's going to be all over 4n squared. And then don't forget the minus 3. And so at this point we just need to do a little bit of simplifying. Distribute the bottom into each thing in the numerator. So 81n squared over 4n squared is going to be 81 over 4. And then I have 160n over 4n squared. The n's will cancel. Yes, I could reduce 162 over 4, but I'm just going to leave it as 162 over 4n. So 1n goes on the top, we still have 1 in the bottom. And then plus 81 over 4n squared minus 3. Didn't really worry about simplifying this 162 over 4n because the next step in this process is once I have it all expressed in terms of n, I take the limit as n goes to infinity to get my area. So we do the limit now as n goes to infinity, and anything that's divided by n, the 162 over 4n here, 81 over 4n squared, they're just going to all disappear. They're all going to go to 0. And we get 81 fourths minus 3, which is 69 fourths. Now, one quick word on this function here. One quick word on this function. So we got our area here of 69 fourths. And so now if we look at the graph here of y equals x cubed minus 1, one of the things I want you to notice is this graph is actually not always positive. So we've actually not computed an area here. We've actually not computed an area beneath the curve, because some of the curve is actually negative. So when we used our formula, we were actually creating negative area. In fact, here we have it. This area here, the portion between 0 and 1, graph's actually below the axis. So that actually gives us negative area. And then the portion of the graph between 1 and 3, that's positive. And so that's giving us a positive area. And so when a function's not always positive, then when we do this definite integral or set up these sums, what we're actually finding is the difference between the area above and the area below. And what I believe we'll find out if you went back and did this, did the area or the integral from 0 to 1 of this function, that's going to give you your -3. That's your -3 area. And then the area above here would probably give you your 81/4. You might want to sit down and work that out for sure. I'm guessing that that's what's going to happen. I haven't actually sat down and computed it myself, but it does make a little bit of sense here that if you did from 1 to 3, you get maybe 81/4 as your area. If you did from 0 to 1, you probably end up getting that -3. Okay. All right, so hopefully that kind of gives you a little more idea how to work these problems out, as well as a little bit of an understanding of what we're actually finding when we're dealing with a function that isn't always positive.